This is my work in progress motion control system. I'm using this to gain a better understanding of how closed loop motion control systems like servos work, and to try to build a better servo. So, for cost reasons, I'm using all low cost components in this prototype build. So, I've got this DC motor here I got off eBay. It's a 12 volt DC motor rated at I think 1 amp, and it was $3. Then I've got this aluminum coupler here. Uses set screws at 45 degree or 90 degree angles rather, and it was a $3. And then I've got this $10 rotary encoder here, and this is a incremental optical rotary encoder, which using quadrature encoding gets 1600 pulses per revolution, so it's very accurate. The motor is being driven by a dual H-bridge driver. It's currently running at 16 volts because that's the power supply I happen to have. This was $2.95 off eBay. This H-bridge driver is being driven by an Arduino, which is also what the rotary encoder is feeding into. I also have a potentiometer hooked to the Arduino for choosing a desired set point. And the set point I'm choosing is velocity, because this is going to be the inner loop of a cascade servo PID loop system. It'll be driven by the outer loop, also known as the master loop, that will seek a position. Instead of the position loop feeding directly to the motor control, instead the position loop feeds to an inner loop that drives the velocity at a precise rate. That way, the outer loop has a desired position, and it sends the inner loop, a velocity to approach the position, and the inner loop worries about reaching and maintaining that velocity. So it allows much tighter control, faster response time under a dynamic situation of loads. So the way this is set up is I use the potentiometer to select a desired set point, and at an interval of every 10 seconds, the loop will run, and it will dial in the desired set point, feed it into the proportional integral loop, and it'll drive a velocity. The way I extract velocity from this rotary encoder is I measure its position, and I take note of the time. Then I measure its position again, and take note of the difference between the position and the difference between the time of the measurements, essentially giving me the derivative of the position, which is the speed or velocity. So now I will dial in a set point and watch the motor respond. So the red line is the set point, and it's hard to tell, but the green line is the actual encoder input. So ideally they would lay right up on top of each other and everything would be yellow. The areas where it's green and red is because that was a velocity outside of the desired set velocity. You can see there's a lag time on deceleration because the motor has inertia and it does have to decelerate. It can't stop instantly. I need to look into braking and see if I can maybe stop it even faster. But for now, it works pretty well. There was some initial overshoot at the beginning, which I'll try to show again. There we go. So there is some overshoot, but it's quickly compensated for and doesn't seem to exist in transients. So the response is really good. That variance is in the single digits of RPMs. So the velocity is pretty tightly controlled, and I'm pretty happy with the way this turned out. And at more casual rates of velocity change, it's nearly perfect. And this is much more typical of a real-world scenario. So, that's it.